So in looking at an op amp like this with negative feedback, and if we're interested in all the nodes and voltages, sorry, all the currents and voltages on all the nodes around here, we could, or I should first remind you a couple of things. Well, let's see. First, so our input is 1 millivolt, our R2 is 50K, R1 is 1K, R2, or the load, I should say, is 2K, and we have an ideal op amp, so it has infinite gain. Let me just remind a couple of things here. So V out is equal to VID times A. So the gain is infinite. That means we could write it as V2 minus V1 is VID, the difference between the two inputs. And in the nomenclature here where I used V minus and V plus in those two nodes, then we would have V plus minus a V minus times A. And let me make a more attractive color. And so that I could separate that and write it as A times V plus minus A times V minus. And if we rearrange, we've got, we can solve for, we can just say that we've got V minus, so that's the voltage on this node. Just want to remind you how the that short works. V minus would be, this is V minus right there. So A times V minus. V minus would be A times V plus over A, so the two A's cancel, and minus V out over A. And so we get V minus, the inverting input node is V plus minus V out over A. And as A goes to infinity, we just simply have this node here is equal to this node there. That's the virtual short. And I always think you should draw that in. And so I'll just draw it in. That's the virtual short. It means that the voltage on node on V minus is the same as V plus. It's not a current, and it's a little different from a short because it's only one way. It goes this way, not that way. Doesn't go the other way. Why is that? Well, Vref is driven. It's an ideal voltage source in this drawing. So, excuse me, it's driven by this voltage source. So V plus has to be this voltage of what Vref is in this case. But V minus is driven by both this power supply here and the output of the op amp, which means that the op amp can adjust its voltage so that V minus will follow this relationship here. And that's what it does. That's the virtual short. It operates as something that will reflect kind of one-way voltage. So it's maybe really misleading to say a virtual short, but it's the nomenclature. V out is set by the op amp to be V minus, whereas Vref sets V plus. And that's probably a more correct way to think about those things. So we might have this long list of things to find. And when you see this on a test, you should be happy and confident because a bunch of them are just kind of by inspection. So for instance, I plus, this current right, let me change colors. I plus, this current right here, well, that's going into the op amp, and if it's an ideal op amp, then that's got to be 0. So I plus is 0. And the same thing with I minus, it's the current going into the op amp here. So that's got to be 0. And I1 feeds directly into I2 because I minus is 0. And by KCL at this node right here, that means that I1 is equal to I2. So you can just, start off the test and write some of this stuff in. We know by the virtual short that V minus has to equal V plus. So in that case, that would be ref. And this equals V ref, which I've given here as being, did I give a voltage for V ref? Well, let's make V ref, what do I want to make it? I want to make it minus 2 millivolts. So your VREF is minus 2 millivolts. Those are like givens. They're really simple things, but I still want to find these powers, and I want to find some more currents. So we do have to do a little work to get those. So I1 I1 times R1, that would be the voltage drop across that resistor R1. That should equal the difference between the two nodes. So that's Vn minus Vn minus, which would be Vn minus Vref, which is equal to 1 minus 2, 1 millivolt minus 2 millivolts, or that equals, that voltage drop is minus, or is 3 millivolts, plus 3 millivolts. So that means that I1 is 3 millivolts divided by R1, which is 1K. We've got 3 microamps. So we can write that in. And then I2 is the same as I1. So then we can go straight on to getting V out. V out is V minus, plus a minus I2R2. I got to do plus because I drew this current is going into that node, so it's got to be the opposite. So that equals, we have Vref on V minus, so that equals minus 0.002, minus 2 millivolts, minus 3 microamps times 50,000 ohms. That's in R2. So that would be minus 0.002 minus 0.15 volts, and that equals minus 0.152 volts on V out. Does that seem right? Does that seem crazy? What's happened there? Well, VREF is something that we could use to adjust and get rid of an offset voltage, which we'll talk about soon, depending on when you listen to this. Or it could be some other reason. This could be used as a comparator. There's various reasons that we could do something like that. So anyway, that's what the output would be. If it seems confusing, we could do it by superposition. So that means for Vref is equal to 0, then we just have the inverting configuration. If we set this voltage source to 0, then we've got the output that we know as V out is equal to, let's call it A, or called A. It's minus R2 over R1 times Vn, which is 50 times, wow. It's 50 times Vn, and Vn is 0.01, 001. So we get minus, minus sign, minus 0.05 volts. And B, set Vn to 0. That's this now becomes, if we set ground here and apply a voltage on that input, then we've got nothing but the non-inverting configuration. So if you can't see that, then just think about it for a minute. So then that's 1 plus R2 over R1 times Vn, or times a Vref. And that would be 51 times 2 millivolts, negative 2 millivolts. So we would get minus 0.12. And we combine superposition. So we have V out A plus V out B. That equals minus 0.05 minus 0.102. And that equals minus 0.152, which is what we got here. So they match. Checked it was okay. So hopefully if one of those two would convince you that's what it really should be. So now that we know V out, we can find IL, the load current right here. So IL, let's go to a different color yet again. IL is equal to V out over RL, which is minus 0.152 volts over 2000 ohms, which is minus 76 microamps. And then we can find I out, which is this voltage right here. We can find I out by KCL from here and into there. So they will sum IL is equal to I out plus I2. And we know I2, so then we can find I out. I out is IL minus I2. So that would be minus 76 microamps minus 3 microamps. 3 microamps. So I get minus 76 minus 3 microamps, where we get 79 minus 79 microamps. So I out is minus 79 microamps. Now think about that. That's what the op amp is supplying. Or if you wanted to think of it, it's taking in, right? The op amp is pulling in that current. It can both supply and it can send current out. It can bring current in. It can do it either way because of the way we would build the power supplies and the op amp itself. Or that's the way they're usually built. So then we could do some powers. The input power is Vn times I1. ignoring VREF, and there wouldn't be anything there anyway. So we have 0.01 volts times 3 microamps, where we have an input power of 3e to the minus 9 watts, or 3 nanowatts. And I'll just do it quick here. The output power is V out times I out. And so we would have minus 0.152 volts times minus 79 microamps. And that gets us 12.008 microwatts. 3 nanowatts and 12 microwatts. They're not big powers by any means. It certainly wouldn't be stressing most op amps to do this, but that's what they are. So when we could find this power gain. So the power gain would be P out over Pn. So we've got 12.008 e to the minus 6 over 3 e to the minus 9. And that gets us 4,003 watts per watt, or in power. That would be 10 log of 4,003, or 36 dB, which is a pretty good gain. And it looks like I forgot to get to the closed loop gain there. And that's just, since we have an inverting amplifier, it's just going to be minus R2 over R1, or that's 50. The reference voltage doesn't actually, no, wait, maybe I should think about that. So the reference voltage will actually change things. So it's minus 0.152 divided by an input voltage of 0.001. So we have a gain of 152. That's a little misleading. That is the closed loop gain. So I've got an example that you can try and work some problems from this as well.